Okay, since you are recording, good afternoon, guys. Um, at least here in Italy is afternoon. Um, I opened this YouTube channel. This is my first video. I'm very excited. I'm not professional, as you can see from my headphones, and now I also have several computers. I'm using the oldest one, but yeah, this is a test, a first video. Let's see if the channel has some. I see the channel has some, I don't know, some audience, and you like it. I will invest in it. I will buy another microphone, maybe. Yeah, for the moment, as you can see, I'm working on Ubuntu, and I'm recording from OBS Studio. First, I'm sorry, I'm not English mother tongue. I hope everything I say will be clear enough, and you will understand it. Why I opened this channel, which is called Useful Algorithms in Python. Useful Algorithms. Because I see many channels on YouTube who focused, some of them focused on operations research, which is a very niche topic, I think. Some of them focus on very basic stuff like data structures. They teach you how to use Python, how to use pandas, how to program. This will be a little bit more advanced. This is more advanced. Yeah. What I want to do is I want to present you some algorithms which are useful, as you see from my from the title of this channel. So what I mean with useful algorithms, the algorithms which are usually presented in other YouTube channels are very basic, like Dijkstra, or for example some sorting algorithms. But this kind of stuff in real life is not that useful. Maybe you need it for some interviews. I've done some in Facebook, Amazon, but in real life you don't need them. Other guys, I really like Coding channel. They focus more on systems engineering, system programming, programming language development. I don't have a background in computer science, so that's not my topic. I'm not that experienced in that. I really watch them. I'm studying also in that direction, but it's not the topic of this channel. In this channel we will focus on algorithms. So in part we will be inspired by operations research problems, but we will implement more heuristic and meta-heuristics algorithms, which are the more used in industry. In particular, if you check my GitHub page, you will find some examples. Here, this is my GitHub page. We will focus, for example, in things that concern especially logistic and manufacturing optimization, but you can have also other application of these algorithms. For example, those algorithms we used for job scheduling. So which machine does which job in which time window, are the same basically used, for example, by the Slurm or AWS scheduler to schedule the job, the requests. Okay, so they find many applications. As you can see, today we focus on an algorithm for supply chain, for logistics and stuff, but please tell me in the comments if you want me to focus also on something else. Yeah, 2D packing, or as you can see here, 3D packing. We will work a little bit also in this direction. Very nice picture, this one. Yeah. Okay. Today we will start from this one, which is the Clarke Wright Savings algorithm. Clarke Wright Savings algorithm is used to solve the vehicle routing problem. So vehicle routing problem, which finds a lot of applications. As you can see here, what is basically the vehicle routing problem? So we have a depot, which is usually represented as a central node. Yeah, this is a nice picture actually. Okay, yeah, let's open it. No, this is the paper. Wow, no. Okay, so we have a depot, and from this depot there are some vehicles, here you see in different colors, which are supposed to start from this depot. They have to visit some customers and then come back to the depot. This is a problem which is faced every day by shipping companies, by Amazon to bring you stuff of Amazon Logistics. So a solution to this problem should tell us which vehicle visit which customers, and also, that's a further step, the order in which the customers are visited, because this is very important and has a huge effect on the total distance that vehicle is running. The objective is, of course, to conclude all the shipments as soon as possible. So we want to satisfy our customers as soon as possible. There are also some constraints on the vehicle's capacity or on the maximum length of these routes, on the routes that each vehicle does. And at the end of the day, at the end of the tour, the vehicle must come back to our depot, okay, and go to sleep, ready for the next day. I've also downloaded actually some benchmarks here. So let's see. Tests. I will put then everything on GitHub. I'm not that fast, that good at coding, but I hope to be clear. Let's say clear. Yes. So let's open just one benchmark, for example. Okay, this is one benchmark. As you can see, each benchmark is a text file with these characteristics. I've already written the function to read it so that we'll go direct to the algorithm, right? So n is the number of nodes, m is the number of vehicles we have, Tmax is the maximum distance each vehicle can run, and then we have all the nodes. For each node we have the x coordinate, the y coordinate, and the demand. We will not use this third value today. We will suppose the first node to be the depot. This is just a convention, but it's okay. And the other nodes are the customers to visit, right? So let's start implementing this Clarke Wright Savings. If you have any question you think I should focus more on the problem explanation, maybe I can do also a further video where I explain the problem with some pictures, slides. We will face many problems and many algorithms to solve these problems in this channel, but everything will be very, very useful in industry. I'm not a real computer scientist, but I also have some knowledge in other stuff, for example, hashing, hacking. So if you want me to focus on those stuff, please tell me. I'm supposed to, and I think to do also some videos in that direction too. Good. So, as you can see here, I've already implemented a problem class. An instance of this class will be a problem to solve, just to standardize things. Standardization, very important standardization. What is this? I don't know. Let's close it. What's this? Okay, yeah. We can delete this one. Yeah. That was a test video. So this function, this method, read problem, is the function we use to read a text file. All the text files are here. So we read the number of nodes, the number of vehicles, the Tmax, the source. We instantiate the source, so the depot. Let's call it depot by source. Depot and depot. Oh, and here let's call it depot even in the problem class. Yeah, okay. Yeah, so the first node, as for convention, will be our depot, and the other are nodes to visit. What the problem has are depot, nodes to visit, and a matrix of distances. What is this matrix of distances? Is a matrix where dists have a problem with this button. Next time we'll use the other computer, where the element ij is the distance from the node I to the node j, right? And in our case, the node 0 for convention will be the source. So dist 0j is the distance from the depot to the node j, and I0 is the distance from the node I to the depot, right? Okay. Maybe from the next time I will stream in live so that I can see if you have questions and stuff. That would be also a good idea. Okay, so what we need is also this Euclidean distance between nodes. So each node has an x and y coordinate, and we calculate the distance between nodes using the Euclidean distance. Again, this is just a convention just to build up our problem. I've also implemented already the node class. So the main classes we will need, let's write them, are basically node, then we will need the edges, which are the connection between nodes. Then what do we need? A route, which is the path each vehicle is doing. And then the last class, I think, is the solver, which is the, well, let's call it CWS, which is the Clarke Wright Savings algorithm implementation. And then again, what do we need is the main.py, the main file, so the starting point for our algorithm, for our program. Okay. Okay, let's check a little bit the node class. As you can see, each node has a unique ID, the x coordinate, the y coordinate, and the demand. We will not use this value, so let's write a comment here: not used, not used. Okay. Actually, we are going on slowly. I hope I will have time to conclude. If we don't, I will restart another video the next time. Well, no problem. Okay, then for each node we save the route the node belongs to, the distance to the depot, and the distance from the depot. These are just used by the Clarke Wright Savings algorithm. Okay, so actually these distances we can already write them. So to depot and from depot, when we instantiate the node we already have this value. So to depot and from depot, right? And here in utils, when we instantiate the node, we can write the distance between that node and the depot. So for the source, they are going to be 0 and 0, and for other nodes, they are supposed to have a value. So let's calculate it. We say to depot equal to Euclidean between the depot and this node. Yeah, actually we don't have them. We don't have them now. But what we can do, we can save them here already. So let's say node is a node. Yeah. n to depot is Euclidean n depot, and n from depot is Euclidean. You will see later why we need these values. So this is just the distance between a node and a depot. So depot node, yeah. Yeah, what we need to change now is this. Good. So we just set them to 0 at the beginning, doesn't matter. Yes. And here we have to remove them also from the source. Good. Yeah. Okay, now we need to calculate this matrix of distances, okay? And I was already doing it here, as you can see. So I will use iter tools. I very bad memory, so let's see what iter tools does. Oh yeah, iter tools. The tools. I think we need the permutation will be good. Yeah, we don't need the values AA because we will start. So let's open it. Our matrix of distances, this can be a numpy array made of zeros. So numpy zeros. What is the size is number of nodes. I don't actually know in the benchmarks if n nodes also include the source, because we need also the source in the matrix of distances. So here we have 32, and here we have 1, 2, 3, 4, 5, 6, 7, 8, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, so the n includes also the source. Good. So n nodes. N nodes. This is the size of our disk. So the distance from each node to itself is already 0. That's the reason why we can use permutations. In this case we could use also combinations, because the distance from A to B is the same distance from B to A, but it's okay, we are just doing some more iterations, and here in the creation of the problem is not that crucial in terms of performance. So permutations. Permutations. Permutations of what? Of source plus tuple nodes. Yeah. So this node 1.ed, node 2.ed will be equal to Euclidean node 1, node 2. Yeah. Let's see if it works. So let's write the main problem. Import utils if name equal to main. La. So we can use OS to have the all the benchmarks in the directory, the list of all the names. So it should be file names, OS dir list, something similar. So we are in source, so we need to go back and open tests. Yeah, let's see, print file names. Python main.py. Dir list, maybe it's list dir. Okay, yeah, so we have all the benchmarks here. We can pick, doesn't matter, the first one. So we can say utils dot read problem, file names 0, so the first one. Okay, and this will return a problem, an instance of the problem class, and we will print the problem dot this, just to see if we correctly compile the matrix. Oh, we have a problem. Not such file or directory. Yeah, that's correct, because we need to give it also the path. So yeah, okay, here is yum tests. Yup. Okay. Name source is not defined. That's true. Because we call it depot. So depot, yeah. Source is not defined. Yes, because we called it depot. That's the. We needed some refactoring. Yeah. So notes this. Oh yeah, we are passing also the file name here because it's a copy and paste from our previous work. So yeah, let's say the file name self.file name. It's okay. Now this is not good because all the distances are 0. So why? Print node1.ed. Oh yeah, that's true. We are never including the node created in the set of nodes. So nodes append n. Okay, good. So yeah, the diagonal seems 0, so it seems correct. We can also actually plot this program just to have a better representation. So we can write a method here which is plot problem. Yeah, before starting the algorithm, it's good to have this kind of stuff just for debugging also sometimes. We can use networkx. So import networkx as an x. And also for doing the matrix of distances is also good to use networkx. So g nx.graph. Then we need a position of dictionaries. Networkx is a famous Python library. If you don't know it, networkx to plot graphs, plot graphs. Yeah. Okay, so positions is going to be a dictionary. So I just copy and paste this. For node in iter_tools.chain, this stuff. We will add pos. Let's say also enumerate, just to also have the ID of the node. So pos node ID. Actually we don't need enumerate, but yeah, that's okay. Node.x, node.y. This is going to be a tuple, because if we pass this dictionary to networkx, it will plot the nodes exactly in the position in which we want it. And we have to say g.add node.id. I don't think we need anything else here. So let's check how is to plot the problem. Networkx plot graph drawing. Yeah, should be an x draw. Yeah, with some arguments. So let's see if I will remember. Draw g pos is equal to pos. We don't need edges for the moment because we already calculated the matrix of distances. networkx is actually good because here well, it's okay. Here we have the Euclidean distance between the nodes. networkx, once given the edges, so the connection between nodes, is able to use the A** algorithm or Dijkstra or Floyd-Warshall to give the minimum path between a node and the others. But in this case we don't need it. Yeah, I'm thinking also to a problem I did yesterday. Maybe I did find something wrong. I worked on a project where I used the networkx to calculate the matrix of this. I need to check actually. I will check. Let's see here. Our video is going well, hope. Okay. So colors, I want to pass also the colors. The colors are a list, so colors are going to be a Python list. I can also copy and paste this stuff from a previous GitHub work. So what can I do? What do we do? So come on, mouse, come on, don't abandon me. Very bad stuff today. Okay, networkx. As you can see, yeah, here where I calculate the matrix of distance. This is a project I was talking about, because I had the edge between the nodes. but that edge is exactly the Euclidean distance. So yeah, we actually don't need this network X in this case, but well, I will correct it. But I want to see, okay, so node colors, and I will also copy and paste this stuff. So yeah, node colors on nodes colors, node color, single, node color, good. So actually it's better if we instantiate it here. No, it's okay. The first is always the source. So problem.depot and problem.nodes. Quietly distracted usually, I don't know. I'm more concentrated when I work without talking. Maybe I'm not a good streamer. So what we need here is nodes color, and we will repeat this problem dot n nodes -1, because yeah, okay, and this is node colors, and source color is given by source color. Very bad code here, but I don't care, it's okay. Source colors plus nodes colors, yeah, it's okay. Let's just see if it works. We need actually to import matplotlib.pyplot as plt. Fig size standard will be, I don't know, 8, 10, 8. Okay. Plt fig size equal to our fig size plt.show. Yeah, okay, so in the main file, once we have the problem, we can say utils.plot problem. Let's see what we have to debug clear. Colors is not defined. Why? Oh yeah, colors. Okay, it's weird that they are so well in position. I don't know if this is a bug or is a characteristic of this problem, because it could be also a characteristic of that problem. So yeah, here I think this is the set of more standard or more regular problems. So we can say sorted file names. In this way we will have the first one. Let's see what happened. Okay, yeah, seems correct. It's okay, good. So as you can see here, we will have many of these problems, which are all the benchmarks we have here. Each of these problems has some characteristics which are not only the number of vehicles and the position of nodes, but also their disposition in space, right? So the pink one is the depot, and the blue one are the customers to visit. Good. So, yeah, I think today we will set up all the stuff we need to implement the algorithm, and I will do another video, a second video, where I really implement the algorithm. So the Clarke Wright Savings, we will have 3 videos dedicated to the Clarke Wright Savings. I will put this in the comments below our video on YouTube, so that you didn't discover it right now like me, but you know it already at the beginning, because actually here is Sunday and I'm going to have a girlfriend. Yeah, I have a girlfriend even if I program. That's weird. Okay. Okay, what do we need? So the node here is ready. Since we are here, we can also implement the edge class. So edge. So the edge are a connection between 2 nodes. Okay, so we have an origin. Let's call it E node and J node, starting node and ending node. Each edge also has a cost, and a saving, but the saving is self-calculated by the edge. So self.enode is the starting node, self.jnode is the ending node, and self.cost is the cost of the edge. So basically it will be the distance between the 2 nodes, right? Yeah. So the saving, what is the saving? Because the algorithm is called Clarke Wright Saving. So let's explain this concept, which is very, very important. Clarke Wright Savings representation. Let's see if we have something good here. Yeah, so look at this picture, which is very, very clear. Okay, so we have a depot, which is the square, and 2 nodes. Okay, so imagine we have 2 different vehicles. One is going to the first node and coming back, and one is going to the second node and coming back. Okay, what happens if we, as in the second picture, we merge? These are 2 different routes. These are what we call routes, and the algorithm basically merge the routes through an iterative process. So when we merge these 2 routes, what happens? We delete this edge, so the edge going from the first node to the depot, and the edge going to the depot to the second node, and we replace them with the edge which is going from the first node to the second node, right? So which is the saving we get doing this thing? Basically we save the distance. We save means we don't have to run the distance from the first node to the depot and from the depot to the second node. But we run the distance from the first node to the second node. So the saving of each edge, self.saving, is going to be E node, so E node, the connection to the depot, so to depot, plus J node from depot, right? Because we are deleting, we are not doing these 2 distances. What happened here? What the hell? Come on. Oh, I changed the mouse. Change the mouse. Okay, let's remove it. Fuck off. Stupid technology. Woo! Okay, good. Much better. Okay, we are not doing this and this, but we are doing this. So this saving, because it's a saving, we don't do this, but we do this. So cost, right? That's it. We can construct these edges here, where we construct the problem. We can pass the edges to the problem. Pew pew. So edges, right. And here, edges, right. So let's see. Here. We can do it here. So let's initialize the edges. Edges is a Python list or a collections.deque. Okay. Edges dot append. We need to import the class. So here we have the import node and import edge. So each edge dot edge, right? Yeah. So cost is this, the Euclidean distance. Node 1, node 2, cost. That's it. But we don't want here the edges that goes from the depot to the nodes or from the nodes to the depot. Okay, so what I want to do here is a check. So we append the edge to the set of edges only if node 1 is different by depot and node 2 is different by depot, because we don't need these edges, we don't need them. They are just introducing further iterations. So let's check if this works. Oh yeah, let's say, well, we don't need to plot the problem again. We can say print for age in problem. What the hell? What happened? Why? So for age in problem dot ages, print age. Okay. Well, we can also write a representation for this edge. Def rep self. This is supposed to be a string, so return f string. Yeah. How we can write it? Just like this. So let's say enode self.enode.id and self.jnode.id. Yeah, let's see if it works. Good. So as you can see, we have all the edges. Yeah, except for the edges we never see the ID 0, because 0 is the source, right, the depot. So it's correct. We didn't want the edge connecting, as you can see, 0 is the diploid, so we didn't want the edges connecting nodes to the diploid. Okay, so now we have all the material to implement the Clarke Wright Savings, and we will do it in the next video. Fuck off, I have to go out. So guys, I hope you appreciated this video. If I see I have some followers, some people interested, I will go on. I also will buy a better microphone. Maybe I will prepare also a little bit more in advance the stuff we are going to do. Hope it is clear to you what is the vehicle routing problem and what is the Clarke Wright Savings. If you're not interested in this kind of stuff, just write a comment. I will read all the comments and try to focus on things you are more interested in. But again, the name of the channel is Useful Algorithm, so we need to focus on useful algorithm. Don't ask me to write the bubble sort. Nobody in industry wants to see the bubble sort. It's never used. Okay, so that's the point. Cheers, thank you guys, and see you for the next video.